Hello students, it has been quite a while since I did not put up my video lectures, but I'm being very honest that I had to work on a machine which I could access after a very long time, and I had to finish the work in about 7-8 days time, and there was a lot of work for it, and I had to finish it, and I had no way out. And I wrote to you apologizing for not uploading my videos earlier, but I think I will compensate it. But at the same time, the work was very much necessary from a PhD student. She suffered a lot from the pandemic, and I think as a teacher, it was my duty to attend that and then to compensate for your class. I hope you will excuse me for it. And I will try to compensate whatever I've lost. But it was a difficult decision for me not to take the class at the appointed time. Right. Now, so we move over to the system that we were discussing so far. We were talking about the CaO, MgO, SiO2, H2O, CO2 system. Now, the important part of this is the vapor part, H2O, CO2, and from the derivation you must have noted that H2O plus XCO2 is taken as equal to 1 in constructing the phase diagram, which means we were talking of fluid present situation, and we will discuss it on the basis of that. It is very well possible that H2O and CO2 do not add up to 1. But that will be slightly more difficult, because in that case, H2O and CO2 become both independent variables if XH2O plus XCO2 is not equal to 1. So then it becomes, you cannot do it on an XY diagram. You have to do it on an XYZ diagram, and becomes more difficult to visualize because the reactions now do not occur as lines, but they occur as surfaces. And so it's a little more difficult. So those of you who will be doing research in metamorphic petrology, you will do it, but for the present moment, for this class, I think we restrict it to the system H2O plus CO2 equal to 1. Now, this system, if you see this, is called the system, which is one of the best systems that is taught for understanding metamorphism, and you will see why it is so critical to understand about metamorphism. There are many rocks. One is, we talk of progressive metamorphism of siliceous dolomites. That means dolomite is the rock where you have a little bit of silica. Or it could also be expanded to a situation where you have dolomitic quartzite. That means quartzite is the dominant rock, where you have dolomitic materials inside. So the formula for dolomite, as I have told you, is CaMgCO3 whole twice, and you have SiO2. Now CaOMgOCO2, this can be written as CaO plus, in terms of CaO, MgO and CO2, and this can be written as in the term of SiO2. So you have CaO, MgO, CO2, these make up dolomite, and SiO2 is SiO2 100%. So say, for example, if you take a rock, dolomite 90, quartz 10, then essentially you're taking a rock which is a dolomite and you're adding a little bit of quartz into it. So we call it siliceous dolomite. On the other spectrum, if you can go, you will have, say, dolomite 10 and quartz 90. Now here, quartz 90, it's a quartzite. So you have a lot of quartz in it. Here, quartz is not in high proportion. It's in low proportion. You can as well say, okay, then we can have a rock of dolomite 50, quartz 50. You can certainly use such a thing, but I don't know what its name would be, so that it could be 60, 40, 40, 60, it doesn't matter. But what I'm trying to say is, when you look at these compositions, and you know dolomite contains CO and MgO, molecular weight of CO is roughly 56, MgO is roughly 40, and silicon is 68 plus 28 plus 32, that should be around 60. So the molecular weight of quartz is around 60, CO is roughly 56, or is it 56? Yes, 56, and MgO is roughly 40. Of course, CO2, you know, has a molecular weight of 44. So you can see that when we talk of dolomite 90, quartz 10, then we have higher amount of CO, MgO, and less amount of SiO2. And if you are taking dolomite 10, quartz 90, then you are taking a lot of SiO2, and we are taking a little bit of CO and MgO. So essentially, this difference in mineralogy is essentially a difference in the composition of the whole rock in terms of major element oxides. In terms of major element oxides, here you have a lot of SiO2 and a little bit of CO and MgO. Here you have a lot, very little amount of SiO2 and a lot more of CO and MgO. So essentially, when you are talking of these two rocks or some other variants of this rock, then essentially what you're talking about, different whole rock compositions. That means bulk rock compositions are different. Have you understood? That's the important point to make. And this will be called, as I told you, dolomitic. This is dolomitic quartzite, and this is dolomitic quartzites, and this is quartzic dolomite, or whatever that is. Yeah, I mix that up. But these are sedimentary rocks. These are sedimentary rocks. So if you go to an area, maybe you get a folded band, for example, where you have dolomite 90, of course quartz 10, and you can have dolomite 10. So what you're doing essentially is you're taking two sedimentary rocks, one with dolomite 90, which is essentially dolomite, and you have dolomite 10, quartz 90, which is essentially a quartzite with little amount of dolomite, and they can be co-folded, and say, for example, this is the axial plane of the fold, right? And so that the question is, here, for example, we have two rock compositions which are slightly different, and they can occur in outcrop scale when you go for mapping, and you can also go for thin section scale variations. So you will have dolomite rich layers and quartz rich layers. The quartz rich layers contains a little bit of dolomite, and the dolomite layer contains a bit of quartz. So you can have these variations at the thin section level, in the hand specimen level, and you can have it on regional scale. And what we are trying to look at, the metamorphism of these two different types of rocks, as we increase the metamorphic rate, I told you, from the Greenwich phases to the amphibolite phases, that is the increasing temperature that we are talking about, the TX CO2 diagram which I drew last time. So essentially you are trying to look at, okay, we have these two rocks. If at the Greenwich phases of a dominant rock, minerals are dolomite and quartz. Dolomite and quartz are present in both, but the proportion of dolomite and quartz is different. And it's our now next objective is to try and understand what is happening inside the rock as we change from Greenwich phases at low temperature to amphibolite phases at somewhat higher temperatures across 500 degrees centigrade. That's what is our ultimate aim. But before we do that, I must also tell you, that this system, CONGOSiO2 H2O system, this is not only applicable to progressive metamorphism of dolomitic quartzite or dolomitic quartzite or quartz-rich dolomites or whatever that is, but it is also applicable to certain ultramafic rocks. You know, you have the potential for ultramafic rocks. Say, for example, you can have olivine, orthopyroxene, clinopyroxene. I am giving you idealized composition, not a lot of this thing. Olivine, orthopyroxene, clinopyroxene. So olivine has the formula Mg2SiO4. Orthopyroxene has the formula Mg2Si2O6. And clinopyroxene has the formula CaMgSi2O6. And no aluminium, so you don't have any garnet, because garnet contains aluminium. You don't have any spinel, because spinel contains aluminium. So you don't have those minerals. But if you go to the mantle, slightly lower mantle, you are expected to get, of course, you can argue the sir in the mantle, yes, it's magnesium rich, but there is also a little bit of iron in it, correct? Absolutely, no contradiction there. So you have to extend the system not to CONGOSiO2, but also FeO a little bit. But since FeO in these magnesium rich rocks, where magnesium number is normally greater than 90, so if you would like to ignore the iron, you would still have a completely different assemblage involving peridotites. You will also have websterites or verlites. You can also have, pyroxenites. You can have olivinites. You can have different types of peridotite. They also come into the system approximated to COMGSiO2, but agreed there should be some amount of iron. But that little iron could also be present in your dolomite quartz assemblage, because it's not that dolomite contains only magnesium, it also contains a little bit of iron, and that's called anchorite. But it's always an approximation that we talk to you as students and telling you how to do it. The important point that I was making is, this is not always a progressive metamorphism of siliceous dolomite or dolomitic quartzite. A lot of ultramafic rocks in the mantle form in the mantle, and then you would have a lot of enstatite and forsterite and diopside, which we have left out already. We could have those base minerals. Fine. Now I have talked about one thing here. This I said, this variation in mineral proportion. This variations in mineral proportion induces variations in the whole rock chemistry. This is one thing. There is another aspect to this. Even with this, for example, the composition of the fluid in terms of XH2O is equal to here 1 minus XCO2. In the paper you will see it's written dXH2O is equal to minus dXCO2 because of the derivative form of this reaction. Now, these rocks may metamorphose with an initially same fluid composition. That means all the rocks, although they have diverse mineralogies, they might have different proportion of H2O and CO2 in the fluid, or they could all start with the same proportion. These are two independent variables. The bulk composition is one variable here we are talking about, and the other variable is not a thermodynamic variable. What I'm trying to tell you, that's a different aspect is the bulk rock composition, and another different aspect is the fluid composition. So you can have diverse rocks with the same fluid composition, or you can have the same rocks, diverse rocks with different fluid composition, or you can have the same rock in the field but with different fluid compositions. You will see how it will reflect when we are studying metamorphism, and that is what is important. Right, now that we have, I think we have understood this part, and now we go into a little more of this phase diagram that I drew last class, and last time I uploaded the lectures. But this time we will talk a little bit about it in greater detail. But we will not draw the whole part of the phase diagram. We will start somewhere lower down. And I will draw only a part of the diagram, which I drew before. And then we will try and discuss what's happening. So let's say this is T and this is XCO2. So this is XCO2 is increasing this side, and this is temperature. This was the diagram. This went on to be 1.0, and this went on to be increasing temperature. And this is how the reaction looked like. This is the lowermost part of it, and the reaction numbers are very important here. 1. This is the same as before, so I'm keeping everything same. This is 2. And this one here is 5. And then there was another reaction here. And this reaction was 3. This was the phase diagram. This was 1, 2, 3, and 5. This is the lower part of the phase diagram that I drew before. And we can see, we will be able to see a lot of things when we are discussing this. Just to give you the reaction, I will just draw it, just give me a time. 5 dolomite, 8 quartz gives you H2O. This is the reaction. And this gives you tremolite, 3 calcite, and 7 CO2. That's how the reaction is. And for 2 it was dolomite, quartz, dioxide, CO2. And this reaction above here, which is 3, tremolite, 3 calcite, 2 quartz, 5 diopside, H2O, and 3 CO2. This is how the reaction was. And then we have the reaction 5, which is tremolite, 3 calcite, 4 diopside, dolomite, H2O, and CO2. These are the 4 reactions that dominate this part. So here, just please always do one thing. Please check your teacher out. If he has done any mistake, you have the Google Classroom and you can indicate it so that we all know it. And if you have some questions, I can try and clarify it. But the important point is here. We must be correct with the numbers. So here, dolomite, quartz, and H2O, they react to produce tremolite, 3 calcite, and 7 CO2. As we move up temperature, we have tremolite, calcite, quartz in the ratio 1:3:2. Molar ratio is 5 diopside, no other solid phases. And then you have H2O and 3 CO2. H2O and 3 CO2 are in the ratio 1:3. The difference between these 2 reactions is here H2O is consumed, CO2 is produced as we go up temperature. Here, both H2O and CO2 are produced as we go up temperature. here dolomite and quartz produce CO2 as we go up temperature. And in this tremolite plus calcite, you can see if we go up temperature, we will go H2O plus CO2. So here we produce, in these two cases are very similar. These two cases are very similar, except that here H2O and CO2 are produced in the ratio 1:3. 1:3. That means for this reaction, reaction 3, H2O is to CO2 is equal to 1:3. That means XH2O is equal to 1 divided by 4 is equal to 0.25. For this reaction 3. But if you take the reaction 5, then what you're producing is H2O is to CO2 is equal to 1:1. That means XH2O is equal to 0.5. That is very crucial to understand. Have you understood? Very, very crucial to understand. That here both the reactions produce H2O and CO2. Here H2O and CO2 are produced where fluid is XH2O is 0.25. Here also H2O and CO2 are produced, but in the ratio 1:1 or 0.5. This is as opposed to these two reactions where CO2 is produced in both. Here H2O is consumed and this H2O is consumed. Not consumed means this H2O is transferred to tremolite. Remember, formula for tremolite is Ca2Mg5 Si8O22 OH twice. So this H2O becomes caught up in tremolite as structural water. It's not that the H2O is somehow gone. No. This H2O now becomes held up within an amphibole, tremolite, in its structural form. That means if this reaction is happening up temperature, then H2O, this reaction is a sink, S-I-N-K, sink for H2O. But it produces carbon dioxide. Now, we look at this reaction a little bit. And we were talking of dolomite 90, quartz 10, and we were talking of dolomite 10, quartz 90. That's what we are talking. Dolomite 90, quartz 10, and dolomite 10, quartz 90. This is a quartzite, this is a dolomite. Not 100%. Right? Now, let's say when we start this when we have these two rocks, as I told you, they have two different bulk rock compositions. Two different bulk rock compositions. This is SiO2 rich, this is SiO2 poor, but the CO-MgO ratio, because CaMgCO3 whole twice, CO is to MgO is 1:1. So the ratio of CO and MgO in both the rocks is the same. This is for your information. That CO-MgO ratio in both the rocks is same because CO and MgO are both in dolomite where they occur in the ratio 1:1 mole. So the ratio of CO and MgO is the same, but the proportion of CO-MgO versus SiO2, that changes. So essentially the change is more because of SiO2 variations, not because of CO-MgO variations. Right? Now, in this reaction, if we go from lower temperature, remember this was around about 500 degrees centigrade, so at the Greenwich phases conditions, dolomite plus quartz is present in the rock. In dolomite and quartz are both present in the ratio 9:1. In dolomitic quartzite, it is 1:9. But dolomite and quartzite, according to the reaction, is 5:8. 5:8. Right? So, 8 quartz is consumed for 5 dolomite. Right? And let us assume to begin with the two rocks have the same XH2O value to start with. Same XH2O value to start with. It starts with two different compositions, but it starts with the same fluid composition. XH2O say 0. Let's say XH2 is equal to 0.5, something like that. Now, you see here what is happening. You have the two rocks folded intricately, and you have mapped in the field axial planes, S1, S2, S3 planes, whatever they are. So you have them mapped, or maybe in a thin section scale, or maybe in a hand specimen scale, or maybe in a thin section scale. There's a difference from millimeters, sub-centimeter, to couple of centimeters to several meters. That's the length scale difference between on the outcrop, hand specimen, and thin section. Right. So, if we take dolomite for dolomite, this is H2O rich. This part is H2O rich. So, if you start with dolomite and quartz, now you see here, if I have dolomite and quartz, what is my variance? What is, according to this diagram, what is my variance? The variance is, you can see here, what is the variance? You have a fluid. This by definition is there because H2O plus CO2 is equal to 1. So, what are the components here? You can see what are the components: CO, MgO, SiO2, H2O, and CO2. These are the components. Or here, for example, you don't have H2O because H2O is not here. You can have H2O also because the fluid by definition contains XH2 and CO2. But remember, you can have the same fluid where XH2 is 0. Right? That means XH2 0 means you're on here on this line. And XH2 0 means you're at this end of the spectrum where XCO2 should be equal to 1.0. Let's see what happens. So for this and for this reaction, say dolomite plus quartz plus fluid, CO, MgO, SiO2, H2O system. So you have F is equal to C minus P plus 2. So what are the components? 1, 2, 3, 4, 5. 5 components. How many phases? 1, 2, 3 phase. Plus 2. So that is 4. In this diagram, what is constant? Remember, these are isobaric diagrams. So 4 now becomes equal to 3. Right? What are the variables? You see, normally the variance is 4. But why I have taken 3? Because you know this diagram was calculated at constant P. So P is known. The P is known. So one variable is gone. You have now 3 unknowns. What are the 3 unknowns? Can you tell me? One is temperature, of course. What is the other unknown? XH2O or XCO2. Now you tell me, why this 3? So have I made a mistake here or have I made a mistake here? You tell me that. I set this question for you. I took dolomite quartz fluid, then I took the component CO, MgO, SiO2, H2O, CO2, and I took F is equal to C minus P plus 2. I took how many phases? I took 3 phases, dolomite quartz fluid, because by definition fluid is a phase. And it says 5 minus 3 plus 2, so 2 plus 2 is 4. At isobaric conditions, there are no assumptions. At isobaric conditions, the variance should be 3. But when I look at the metamorphic variables, it's TXH2. T and XH2, I do not see any more metamorphic variables. No intensive variables are present in the rock. Where is the flaw? Where is the flaw? The flaw is in taking H2O. The flaw is taking H2O because H2O is not. This is where the flaw is. I will strike it with the red ink. So you please think about it. These are very crucial questions. No H2O. I don't need the H2O. Why I don't need the H2O? It is because in dolomite there is no H2O. In quartz there is no H2O. In the fluid, if you take CO2, H2O is by definition constrained, so you don't need H2O. If you don't need H2O, then you see your component becomes 4, phases remain the same, 3, this becomes 3, this becomes 2, this is right. That is what is very, very, very careful with metamorphic variance. You have to be very, very careful. First, if you take all this, I take all this, it's a CMGSiO2H2O system, I have taken CMGSiO2H2O system. Right, let's do it. F, C minus P plus 2, C is 4. Initially I took C is 5, 1, 2, 3, 4, 5. You will say, yeah, I am right. Then 3 phases, dolomite, quartz, fluid. Of course, you took fluid as a phase. So 3. So 2 minus 2 is 4. At isomeric condition, it should be 3. And you're stuck with T and XH2. Because XCO2 is 1 minus XH2. You made a mistake in your phase diagram, in your understanding of variance. Why? I don't need H2O. Because H2O is not needed in anything. Here, if you say that I have H2O in the fluid, but it is taken care of because you have already CO2, and XH2O plus XCO2 is equal to 1. This would have been correct. This one that I have struck out would have been correct if fluid absent situation prevailed. Fluid absent situation prevailed. And then also this fluid, you see, it should have been dolomite quartz. If there is a fluid with another component, it would be one thing. A fluid with only 2 components, but fluid absent would have been another thing. So you need to be very careful about the variance. Very, very careful about the variance. So just dolomite and quartz, dolomite quartz fluid, H2O simply goes off. H2O simply goes off. So dolomite plus quartz plus fluid, H2O is not there. The variance now fixed. Of course, both are unknown. That means if you say dolomite or quartz, you have to assign a T value, you have to assign a CO2 value. You have to assign both to find where you are in this diagram. In this part of the diagram, where you are, you need to fix both temperature and XCO2, both. That is very, very important. I will give you another example. If we go to the other reaction, reaction 2, you see the same problem if you handle it. If you don't handle it carefully, you will have the same problem. You see dolomite once again on this side. Again you see here the same thing applies. Dolomite, quartz, fluid. Right? Dolomite, quartz, fluid. Once again, CaO, MgO, SiO2, H2O, CO2. Is it right? If I take this, is it right? No, it's not right. I will tell you why. You see here in dolomite, if I break up this, CaMgCO3 whole twice. That is the formula of dolomite. Right? But I can break it up as CO, MgO, and CO2 in the ratio 1:1:2. So I can CO and MgO, since it does not occur anywhere else, I could take this and put it into one single box, CaMgO2. Do you see that? CaMgO2, because I don't have to break it anywhere. I don't have to break it anywhere. So for this composition, so dolomite, CaMgO2, if you have quartz, then you have SiO2, and then you have H2O, and then you have CO2. So this is also one way how you reduce your component, not 5 here, like we have written, but it is 4. Why? Because in dolomite and quartz, CO and MgO are in the proportion 1:1. So you can club them up and you can generate a fictive component CaMgO2. CaMgO2. So CaMgO2 plus CO2O2 will make your dolomite. There's no problem there. CaMgO2 plus 2 CO2, and that would make up your dolomite. You don't need anything. You don't need anything else. And of course you will have SiO2 because you would require your quartz to be described, and CO2 will always be the term. So that is how you should be very careful about how you deal. Just don't deal things blindly. Okay, if I ask you what is the variance of this, let me give you another example. See how complicated this phase diagram will do work if you don't use it carefully. Say for example, see here. Let us see this reaction. Dolomite, what are the phases? Dolomite, quartz, diopside, CO2. Right? Here, on this reaction, that means I am somewhere on this line where all the four things exist. What are the, if these are the components, then we have dolomite, diopside, quartz, and fluid. This is what we have, dolomite, diopside, quartz, and fluid. Now you see here, when I talk of the components, you can say, I take CO, MgO, SiO2, H2O, CO2. Same as this. Ask yourself, what is the formula of dolomite? CaMg, CO3 all twice. What is the formula of diopside? CaMg, Si2O6. You, for components, you need minimum number of components. Minimum number. So here you see 1:1. So you can take a fictive component CaMgO2. CaMgO2 is the minimum number of components. If you separate them out, you're overdoing the system. You are overdoing the system. So you can have a component CaMgO2. You can have SiO2, of course, because you have dioxide, and you have quartz, and you have H2O, and you have CO2 if you want now. So you have 4-component system, not a 5-component system. Not a 5-component system. You have a 4-component system. And remember this one. And remember the problem with this. None of this require H2O as a phase. So if you go with this way, now you have 4 components. You have 4 components. So your variance should be equal to F is equal to C minus P plus 2. So now you have not 5 components, but 4 components. And you have how many phases? 1, 2, 3, 4. 4. 1, 2, 3, 4 phases. So plus 2. That means you have 2. At isobaric conditions, you have 1. What are your metamorphic variables? T and XH2O or XCO2. XH2O or XCO2. Now you see why you need 1. Because you're on the reaction curve. So if you take a particular XH2O value, your temperature is automatically fixed. You don't need any more variance. But when you are below this curve, the variance was 2. But on the curve, your variance, here for example, your variance, your isobaric variance, actual variance here is 2, the actual value there was 3. So remember, when you are on the phase fields, your variance is higher. When you are on the reaction lines, your variance is lower. It's actually univariate. In a binary diagram, you have univariate reactions. And so you can see this part would have no variance here. We will talk about that later when we read. But what I am trying to tell you is, so when somebody asks you in the CO, MgO, SiO2 system, what is the variance of dolomite dioxide quartz, you have a few things to ask your examiner. Whether he knows chemically. That's the important point. Whether he knows it correctly. And this is a very important part. This part is very important. If you have two minerals with two components which have similar in ratio, then you can club them up to make a minimum number of components. Minimum number of components. You can make them up to a minimum number of components. Because their ratio, like here, dioxide and dolomite, the ratio of Ca and Mg are the same. So if they are same, you don't make CO and MgO. You make Ca MgO2. That gives you the minimum number of components. It is very important to realize this. Just don't use variance blindly. Now let's see. Now we go back to this diagram. I will use the black pen a little bit. Now let's say we have, as we go up temperature from green schist, dolomite quartz field to up temperature across the green schist faces to the amphibolite faces. Your dolomite is to quartz at, depending, you see here, if your CO2 value is here, then the temperature is here, right? If your initial X2 value is here, your temperature is here. Do you see that? This would be the temperature if you start with a higher XCO2 value, and your temperature, if your CO2 value is here, you start at a lower temperature value. Essentially, if you're increasing the XCO2 of your system, dolomite plus quartz are stable at higher temperature. This is very, very crucial. Although both contain dolomite and quartz, both contain dolomite and quartz are the reactants to both these reactions 1 and 2. But dolomite plus quartz will react to give you trebolite plus calcite, not at the same temperature. It would depend on the CO2 content of the fluid. CO2 content of the fluid. In carbonic fluid systems, carbon dioxide rich or carbonic fluid systems, dolomite plus quartz would react at a higher temperature. There, in hydrous systems on this side, CO2 decreases on this side. So in a more hydrous system, dolomite plus quartz breaks down at a lower temperature. So although dolomite and quartz are present in the rock, if they have the same CO2 value, they will start decomposing at the same temperature. But if they have different CO2 values, either the same rock or another rock, they will break down at different temperatures. This is very, very crucial. This is very, very crucial. What is crucial? Once again, I repeat. Let's say you have dolomite 90, quartz 10, XCO2 0.1. And the same rock, dolomite 90, quartz 10, XCO2 0.9. Dolomite and quartz will not react, will react at low temperature, at hydrous conditions. And the same rock will start breaking down to trebolite plus calcite at a higher temperature, if you have a carbonic system. Even if, although the whole rock mineralogy is different. Although the whole rock mineralogy is different, the temperature it will start breaking down to produce trebolite calcite at different temperatures depending upon the fluid content of the rock. In other words, and you can take the other case, say for example, you have dolomite 90, quartz 10, and dolomite 10, quartz 90. Here XCO2 is 0.5 and here XCO2 is 0.5. Now you see there is something interesting. Although both the rocks have different bulk compositions, but they have the same fluid composition, so they will start to break down at the same temperature. At the same temperature. Both will break down. Dolomite plus quartz will start reacting to produce tremolite and calcite at the same temperature, although the bulk composition is different, but fluid composition is the same. The fluid composition is the same, although the bulk rock composition is different. So that are now important. What is it? That whether a reaction will operate will be determined not only by pressure temperature condition, but by the pressure temperature, by the bulk rock chemistry and the fluid composition. Have you understood? The bulk rock chemistry and the fluid composition will control at what pressure and temperature a particular reaction will operate. At what temperature a reaction will operate. That is very, very crucial. There are, again I repeat, that we are talking of two different things. One is the bulk rock composition. CaO is to MgO is to SiO2. Right? And the other thing that we are talking about, fluid composition, is in terms of XH2O. XH2O or XCO. These are completely different things. These are two different things. So whether a reaction will operate, it will be controlled by the bulk, it will be controlled by the fluid composition. You remember these are isobaric sections, isn't it? This is an isobaric section. Remember, it was del T by del XCO2 at constant P. This was the bisobaric condition on which this diagram was done. So at this point, your variables are temperature and XH2O or XCO2 for fluid present situation. If it's fluid absent, this OR will go off and XCO2 will come in. And one more metamorphic variable, unknown, comes in. This is very, very important. So wherever you have fields, no reactions, you have higher variance, and when you are on the reaction line, that means if you have additional phases, you can see from the equation F is equal to C minus P plus 2, if you keep C constant and decrease P, your variance will increase. If you keep C constant and decrease P, number of phases, that means, say this dolomite quartz, then your variance will be higher. But if you increase P, number of phases, then your variance will decrease. So we are discussing important points. That if you have fewer minerals, it's a high variance as such. If you have more minerals, it's a low variance as such. So during metamorphism, the variance of the rock changes. Constantly changes. We will see more of this effect very soon. But this is what is important. You must realize that the metamorphic condition in this rock is not only PT. This is what is told to you. It's not right. The control factor is the bulk composition, and even stronger is the fluid composition. That will determine whether a reaction will operate or not. Of course, I'm assuming there are no kinetic barriers. That's a different issue, completely different issue. But this is very, very important to realize. Fluids play a dominant role in metamorphism and in metamorphic and igneous spectrology. huge role. Okay, I think I will stop here because the new topic will take us to somewhere else. We'll stop here. Next lecture, I will elaborate on that. Thank you.